Hi everyone! Today let's talk about session 1.3, slope field and solution curves. So chapter 1 is about solving differential equations. And actually we're going to focus on solving the first order differential equations, right? And if you can still remember in calculus 1, given any functions, we can always find its derivative, right? We can use product rule, quotient rule, chain rule, all the combinations of the laws to find the derivative. But when you were in Cal 2, you understand there are a lot of functions we're not able to find the antiderivative, right? We learned some techniques like U substitution, integration by parts, trig substitution, partial fractions. But those techniques can only help us to integrate some kinds of functions, but still not all. Okay? So similar to the differential equations, there are a lot of differential equations we cannot solve and get a nice formula. But however, we can kind of draw the solution curves and have a rough estimate of what it looks like. And we can also have theorems to show us when a solution exists and unique. Okay, so today we're going to talk about that. So, given the first order ODE, dy dx is f of xy, so f is a function of x and y. So this is the standard form, okay? The left hand side you have the derivative and the right hand side is a function of x and y. And then we have the initial condition y of x0 equals y0. Okay, so this is the initial value problem. It is the ODE plus the initial condition. Okay, so let's look at the methods of direction field. The direction field, also called slope field, okay, or slope field, is the graph of the directions of the slope f of xy at every point in the xy plane. For example, let's look at this. dy dx equals x plus y. If you can remember from calculus 1, we know that derivative is the slope of the tangent line, right? So given a curve, and this is the point, and this is the slope of tangent line, and it equals to the derivative at, let's say this is x. Okay, so that is the slope of the tangent line. Okay, now let's consider this initial value problem. So at each point, we can put the points into this differential equation, and then we can get a slope, right? For example, if we plug in 0, 0, what happened? So at the point 0, 0, we plug in 0 plus 0 is 0. So the slope is 0. Oh, keep in mind, the lines, okay, like this. So this guy's slope is positive, this guy's slope is negative, this guy's slope is 0, and this guy's slope is undefined. So at 0, the slope is 0, 0, the slope is 0. So we can put a little horizontal line to indicate the slope. And then at 1, 1, you can see 1 plus 1 is 2. So at 1, 1, you can see the slope is 2. So we draw a little line segment there. And then at the point 1, 0, 1 plus 0 is 1. So that's why at 1, and then we have a segment like this. And you can see as the slope increases, our line is more steeper, okay? And when we plug in 0, 1, we also get 0 plus 1 is 1. So here we also have the slope 1. So at every point in the xy plane, we can plug in the differential equation and get the slope. And then once we plot all the small segments, then we can get a slope field like this. Okay, now imagine this is our initial condition 0, 1. So we want to figure out, okay, 0, 1 is right here. Can we estimate a solution curve passing through the 0, 1? Wow, imagine we're following in a water river, and then you can see follow the rivers, then the graph looks like this. Okay, so that's why we get this picture. So this is the solution of the differential equations. So it looks like this. Okay, so the slope field we can graphically draw the solution, right, and estimate it. Okay, more examples. So here y prime equals 1. So it means the slope is always 1. That's why you see this slope field is constant slope, right? And let's say a point, a solution curve passing through, let's say 0, 1, looks like this. Okay. Next picture, y prime equals x. So then the slope field looks like this. And then you can see, okay, if I want to find a solution curve passing through 0, 0, then you can see follow the arrows, we get a parabola. Okay, next, y prime equals y, and then this is the slope field, and it depends on the initial conditions, right? Okay, let's say if our initial condition is right here, then if you draw a picture, it looks like this, right? If our initial conditions is on the x-axis, then can you see the solution curve look like this? And if the solution is down there, so the initial point is down there, then you can imagine the solution curve looks like this, which is exactly like this. Okay, everyone? And then next picture, y prime equals e to the x. And then now you can see, given a points, then our solution curve looks like this. Okay? And how about the next one? Okay, the next one, if the initial point is right here, then it looks like this, right? If the initial point is here, then we can get a line. And if the initial point is right here, then can you imagine the curve look like this? Okay, which is exactly this. And similarly, oops, oh, it shifts when I shift the page. Okay. Okay, next, look at this picture. If our initial point is here, you can see it looks like this. If the, oh, it actually touch the x-axis, okay? If the initial point is right here, then it looks like this. Okay, how about this guy? This guy looks like this, right? And this guy look like that, right? And this guy look like this. Okay, so we can follow the slope field and we can draw the solution curve. And it depends. It also depends on the initial conditions. So that's why the initial conditions, with the different initial conditions, we might get different curves. For example, here you can see you get 3 different curves based on the initial point. Okay. All right. Let's continue. Example: match the differential equations with its direction field. Okay. So here we're doing the matching. So I would say you pick some point to plug in and look at the slope. And usually the point we pick is the 0, 0 because it's easy to compute, right? So here when we plug in 0, 0, what happened? Here we plug in 0, 0, we get y prime of 0, 0 is 2. 2 is positive, but it's obvious this guy, the slope is negative, so of course not this one. And then here as 0, you can see the slope is positive, so it could be this one. Here the slope is 0, so it can be this one. here the slope. Okay, look at this guy. It was like this on the left, it's like that on the right, so in the middle, it must be flat. So the slope should be 0 as 0. So that's why not this one, not this one, not this one, it must be this one. So connect them together. See, we just plug in one point and we can figure out which one. Alright, now let's look at the second differential equation. When we plug in 0, we get 0. So, but we have two pictures with 0, right? Okay, now let's look at it more. This guy is 0 if, so y prime is 0 when x is 0, or 2 minus y is 0. 2 minus y is 0 means y equals to 2. So which means for the slope of this guy, x is 0 means the y-axis. So on the y-axis, it should be all 0. Okay, this guy match. And when y equals to 2, it should be also 0. But you can see here, obviously, this is not 0. So not this one. And then, okay, this one will work. See, as x equals to 0, so y-axis is 0. When y equals to 2, is also 0. Right? So it should be this one. Okay, let's continue. How about this guy? Oh, when you plug in 0, you, oops. Okay, so when we plug in 0, what happened? We just get -1. Ooh, good. -1 slope is negative, then it must be this guy, right? So we can connect them. Alright, so this is right here. And, okay, the last one, it must be this guy. But why? Okay, so this guy is 0 when sine of x is 0 or sine of y is 0. So it means xy is 0. So the sine function looks like this. So it could be pi, minus pi, etc. Okay, now you can see x is 0, that's the y-axis. Y is 0, that's the x-axis. Pi is like 3.14, so around 3. Now can you see it's quite flat? Around 3. And here around 3. Ooh, you can see? Yes, it match. So good. So this is the slope field for the number 4 differential equation. Okay, now we have finished the matching. Alright. Okay, so let's continue. Theorem of existence and uniqueness. This is very powerful because we know a lot of differential equations we are not able to solve it and get a nice formula. But this theorem can help us to have an idea whether a solution exists or whether it is unique. Okay, so consider initial value problem dy dx equals f of xy. So before you use the theorem, you must express it into the standard form. So must express the differential equations as the standard form. So this is the standard form. If it's not in the standard form, then you have to change it. Okay? For example, if you have e to the y prime minus 2x y equals to 5, something like this. How do you express the ODE as the standard form? Oh, basically you just solve for y prime, right? Okay, e to the y prime, we move the 2xy to the other side, and then you divide it by e to the y. Okay, now, so this is the standard form, okay? And we also have the initial conditions. Okay, let's look at the following. If f, so f is whatever on the right-hand side in the standard form, okay? If f of xy is continuous on an open rectangle containing the initial points x0, y0. Okay, so let me draw a picture here. So let's say this is x0, this is y0, this is the point, okay? And then we have like a rectangle there, and x0 is around alpha, beta, y0 is around gamma, delta. Okay, this is like a rectangle. And, oh, it's open rectangle. Maybe I should use a dashed line to indicate we don't want to include the boundary. It is an open rectangle. Okay, if f is continuous on this open rectangle containing the initial points, then the theorem tells us that there exists at least one solution in some subinterval of x and y. So we know a solution exists in some subinterval. Okay, maybe a solution exists here. Okay, in a smaller rectangle. In addition, if partial f partial y, so be careful, this is taking the derivative, the partial derivative of f with respect to y. If this guy is continuous on this open rectangle, then the solution we get from step 1 is unique. Okay? So that's why you can summarize as if f is continuous, then we get solution exists. If partial f partial y is continuous, then the solution is unique. Okay, so what do we need to do to show an ordinary equation has a unique solution? Well, you want to find interval for x and y, where f and partial y are continuous on these intervals containing x0 and y0. Caution, existence, and uniqueness guarantee in subinterval. So the theorem guarantees the existence and uniqueness for the solutions in a subinterval. So you might not get a solution on the entire interval, but you might get a smaller one interval. Okay? Next, the unique solution of the initial value problem is called a particular solution. Every particular solution of a linear first-order differential equations is contained in its general solution. Okay? Particular solution, remember, for linear ODE, we get general solutions, but we have some constant there, like C1, C2. But with the initial conditions, you can plug in and find the values for C1 and C2, then you get a specific solution, a particular solution. Okay? By contrast, it is common for a nonlinear first-order differential equation to have both a general solution involving an arbitrary constant C and one or several particular solutions that cannot be obtained by selecting a value for C. So these exceptional solutions are called singular solutions. Okay, so if the ordinary differential equations is not linear, then we can have like a group of solutions that they're in a particular form with a constant C, so we can still call it general solution, even though this general solution does not include all the possible solutions, but because it has the a format that a lot of solutions appear like this, so we can still say they are general solutions, but we also have one or several particular solutions that is not in that format. Okay, that's possible for a nonlinear differential equations. So those exceptional solutions are called singular solutions. So for nonlinear differential equations, we have general solution plus some singular solutions. Okay. All right, so now let's look at more examples. Let's look at example 3. Okay, we have y prime equals minus y cosine x. y of pi equals 2. Okay, so solve this initial value problem. Show this initial value problem has a unique solution. So we want to use the theorem of existence and uniqueness. Okay, so what do we do first? First step, make sure we're at the standard form. Okay, so step 1, do we have standard form? Yes. See, y prime equals minus y cosine x. So this is the standard form. Then f of xy is the right hand side. Okay. Now second step, we want to look at f. Ooh, look at f. F is minus y cosine xy. Look at y. Y is continuous everywhere. Cosine x is continuous everywhere. Okay, do you remember the special functions with restricted domain? Let me remind you. Okay, so functions with restricted domain. First, square root. If you see square root of a, then we need the a to be greater or equal 0, right? Second, fractions. If we see fractions, we need the denominator is not equal to 0. 3, natural log. What do we need? A is positive. And also we have more, for example, the tangent, cotangent, secant, cosecant, right? And in that case, you have to figure out, depends on the picture of that. Okay, now let's look at this picture. So y is continuous everywhere, cosine x is continuous everywhere, so we can see y. So f is continuous for all x and all y. It continues everywhere for any xy. Alright, so this is good. So it means a solution exists, right? Third, we want to take the partial derivative of f with respect to y. And now what do we see? Okay, x is like a constant. Y is like a variable, right? So this guy means we consider y as variable and x as constant. Okay, now, so y is the variable, so the root of y is 1, so we just get minus cosine x. Oh, cosine is also continuous everywhere. This is continuous for all x because it has no y in it, so no matter what y we pick, the function is also continuous. So that's why solution is unique. Okay, so when you combine these together, this is how you answered. Okay, you say a unique. Okay, you can say by the theorem of existence and uniqueness, a unique solution exists. Okay, in some neighborhood, of the initial point. This is x is pi, y is 2. Okay? And we don't say interval because interval is one dimension. It's only for x or y. Here is like a region around it. And actually, because it's continuous everywhere, so actually the unique solution exists everywhere in the xy plane. Okay, everyone? And in general, there are 3 possibilities how we answer the questions. So what are those 3 possibilities? Okay. So 3 possibilities. Okay, first one, a unique solution exists. Okay. In some neighborhood, blah, 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 blah. Okay. Second, we have existence, but not uniqueness is guaranteed. But not uniqueness is guaranteed. Okay, guys, you have to be careful. Look at this sentence. And let me ask you another sentence. I say solution exists but not unique. Are these sentences the same? Existence but not uniqueness is guaranteed. And solution exists but not unique. Are these sentences the same? No. Why? The left side, we know we can guarantee existence, but we don't guarantee uniqueness. So the solution might be unique or it might not be unique. We don't know. We don't know. So we cannot say it's not unique. We just don't know. We cannot show it is unique, but we cannot say it's not unique. So that's why don't answer like the right hand side. Don't answer. So this is wrong. Don't answer like that. Okay, so you say existence but not uniqueness is guaranteed by the theorem of existence and uniqueness. And 3, if f and partial y are both not continuous, then we say neither existence nor uniqueness is guaranteed by the theorem. Okay, and also this does not equal saying that solution doesn't exist. Okay, we just say we cannot guarantee existence, but the solutions might exist or might not exist. We don't know. We can't guarantee. But you cannot say the solution does not exist. Okay, so these are wrong. Be careful, be careful, be careful. Okay, and when do we come up with these different possibilities? Okay, let me make it smaller. Okay, let me make it smaller and let me move to the right a little bit. Okay, and when do we have this? Okay, so let's see. Alright, let me get a different color. Okay, you like pink? Okay, when do we have a unit solution exist? That is when f partial y are continuous. Then you can get this. Existence but not uniqueness. So you get f is continuous, but partial y is not continuous. Then you get this. Neither existence nor uniqueness is guaranteed. This is when f and partial y are both not continuous. Yeah, that point. Then you can say that. So far, so good, everyone? Okay. And here I give you the picture of the slope field and the solution curves passing through the point pi 2. Okay? And you can see a unique solution exists, and this is the solution curves. Alright, so the theorem of existence and uniqueness only tell us whether the solution exists, guaranteed to exist or unique, but it cannot solve the solution. Okay, so in order to solve the solution, we need to learn some techniques that we will talk about that in session 1.2 and 1.4. Okay, but now because we're looking at this example, I also want to show you how to solve this differential equations. Okay, so here I hope this part you can come back and visit after session 1.4 1.2 and 1.4, right? So when I'm teaching you right now, if you don't understand, you can revisit this part after you learn session 1.2 and 1.4, because in those sessions we will cover more. Okay, so how do we solve this? Let me use a different color. Okay, so how to solve this? Okay, so this differential equation is actually separable. So in session 1.4, we talk about how to solve separable differential equations. But how do we do is we want to move the y on the left and move the x to the right. So this is dy dx. Okay, how do we move the y to the left? We can both sides divided by y. And how to move the dx to the right? Both sides multiplied by dx. Now you can see all the y is on the left, all the x is on the right. We can integrate both sides. And on the left hand side, we have natural log of absolute value of y. And on the right hand side, integral of minus cosine is minus sine x. And then plus c. Okay, and then we want to solve for y, so we can both sides raise to the power of e. So we have e to the e and ln cancel, so we have absolute value of y equals e to the minus sine x plus c, but plus c is the same as e to the minus sine x times e to the c. Okay, in order to get rid of the absolute value, so because y could be positive or could be negative, but this e to the c is only positive, right? So let's rename a new constant. We can rename it as d. So by renaming this new constant, it can take care of the absolute value. So it take care of the absolute value, and also we get back the solution y equal to 0. So you know y equal to 0 is actually a solution of this differential equation, because y is constantly 0, then y prime is 0, so 0 equals 0. So this is a solution. But when you, at the first step, when you divide it by y on both sides, you're assuming y is not 0. So that's why by renaming this e to the c to a new constant, you actually obtain back this solution. Okay, and with this initial condition, we can plug in. So y equals e to the minus sine pi times d, and then y is 2, right? Okay. And what does sine look like? Sine, here, this is sine x. Sine pi is 0. E to the 0 is 1. So that's why d equals to 2. So now we know, our solution. Y is then 2 times e to the minus sine x. So which is this guy. Okay, so this is how we solve the differential equation. And we will visit more in session 1.4. Okay, good. Let's continue. So example 4. Is this ODE linear or nonlinear? So here is the slope view. Why the theorem does not apply? Okay. Alright. Let's see what happened. Okay. So when we try to use the theorem of existence and uniqueness, let's see what happened. First step, do we have the standard form? Answer is yes. Y prime is y to the 1/3, and this is f of xy. Okay, so second, f of xy is y to the 1/3. Is this guy continuous? Okay. So look at this guy. x0, 0. So key roots, what does key roots look like? So this is the key roots. And what happened? This is the key root, right? So the domain is our real number. So this guy is actually continuous for all x and all y. Okay? So now we know solution exists. 3, and then partial f partial y. Okay, chain rule, right? 1/3 y to the minus 2/3. Okay, I actually don't need chain rule in this case. Okay, because it's just y to the 1/3. So just power rule, 1/3 times y to the 1/3 minus 1 is minus 2/3. But negative means it's actually in the denominator, right? It is in the denominator, so we know denominator cannot be 0, but in our initial condition, the y is 0. We're looking at when the y is 0. Oops. You can see this partial f partial y is not continuous. So it's not continuous near y equals 0. Okay, so that's why we have existence but not uniqueness is guaranteed by the theorem. Okay, so by theorem of existence and uniqueness. Okay, existence but not uniqueness is guaranteed. Okay, near x0, 0. Okay, so this is what we can tell from the theorem. Okay, so let's look into this differential equations. Let me try to solve it and let's see what happened. Okay, let me use a green color. Okay, all right, so now let's see here. We have y prime equals y to the 1/3. Okay, now this guy is separable, right? So we can both sides divided by y to the 1/3, and we get y to the 1/3 over y. I mean, this is dy dx. So this is what we get, and so we have integral y to the minus 1/3 dy equals integral 1 dx. We integrate that. Okay, add 1 to it. Y to the 2/3 over 2/3 equals x plus c, right? So y to the 2/3 is let's see, 2x over 3 plus c, and furthermore, okay, we have initial conditions, x0, 0, so we plug in y0 and x is 0, so we get c is minus 2/3 x0. Okay, so y to the 2/3 is 2/3 x minus x0. Okay, then y is, okay, we take the root. Okay, so we take the, let's see, this is x minus x0 to the 3/2. And okay, furthermore, there are actually more information. So this means we take the cube root and then we square. So this guy is always greater equals 0, right? So that's why this formula is only true. Okay, so this formula only works if x is greater equal to x0. Otherwise, if this guy is negative, you cannot take square roots, right? And then here, when you take square roots, see, this is 1/2 is like square root. When you take square root of a positive number, you actually get 2 roots. You get plus or minus. So you actually get 2 roots here. Okay, so this is square root. Okay, so what happens? Okay, what does that mean? So let me draw let me draw some picture here. Okay, so keep in mind we have y prime equals y to the 1/3. Now I want you to consider y equal to 0. So this is a line. Okay, and then do you realize y prime is also 0? So 0 equal to 0. So y equal to 0 is a solution. Okay, so let's go back to this picture. It means y equal to 0. So that is this x-axis. So this is a solution. Okay, so this is a solution. And furthermore, let me draw. Okay, furthermore, if we defined y to be 0 if x is less than equal to x0, and we define it as 2/3 x minus x0 to the 3/2. Okay, if x greater equal to 0, then you realize this is another solution, because on this part it satisfies the differential equations. On this part it also satisfies the differential equations. So this is a solution. Okay, and do you know what this guy looks like? This guy looks like let me draw the picture here. So this guy looks like this. Okay, so it's increasing. Alright, so now we have one solution, two solutions. Actually, we can have one more. And what is that solution? We can define it to be 0 if x less than equal to x0, and we can define it as minus 2/3. Oh, sorry, I forget the parentheses. 2/3 and then x minus x0 to the 3/2. Okay, if x greater equal to x0, then this solution corresponds to this guy. Can you see now, passing through the same point, there are 3 different solutions? So you can see 3 different solutions. So that's why solution is not unique. So solution is not unique. And actually not unique because we solve the differential equations and we also combine the picture and we can figure out this. But the theorem of existence and uniqueness doesn't tell us the solution is not unique. It just tells us we don't guarantee the solution is unique. But we actually need to solve the differential equations and look at the picture and then come up with these 3 equations. Then we can say the solution is not unique. Okay, everyone? You know the differences? The theorem of existence and uniqueness only tell us whether we guarantee the solution exists or unique. But when it does not exist or when it's not unique, we cannot say by the theorem. We have to go deeper into the differential equations and figure out that. Okay? Alright, so this is example 4. Now let's look at example 5. Okay, so is this guy linear or non-linear? Oh, this guy is actually linear. Oh, did we answer the last questions? The last questions, this guy is non-linear, right? Because cube roots non-linear. But then this guy is actually linear. See, y prime and y. So yes, this is linear. Is there a unique solution? Okay, let's check. Okay, first step, what is that? Standard form. And yeah, it is in the standard form. So So in this examples, you can see I was giving you standard forms, but in the exams, I might not give you standard form. Then you have to solve for y prime to get the standard form. Okay, so y prime is y over cosine x, and this is f of xy. So f is y over cosine x. Okay, this guy is continuous for all y, but when the denominator is not 0. Okay, and what is cosine? Cosine looks like this. When cosine is 0, so which means x cannot be, this is pi over 2 plus k pi, where k is integer. And oh, you see what happened? Our initial point, x is actually pi over 2. So that's why this guy is not continuous at the point pi over 2 pi. So okay, and furthermore, partial f partial y is derivative of y is 1. So 1 over cosine x is also not continuous at the point pi over 2 pi. So that's why, because they're both not continuous, then we say neither existence nor uniqueness is guaranteed. Okay, so neither existence nor uniqueness is guaranteed by the theorem of existence and uniqueness near the point pi over 2 pi. Okay, now we have seen 3 possibilities, right? We have saw this one, a unique solution exists. This one, solution exists but not unique. Not uniqueness is guaranteed, right? And then this one, neither existence nor uniqueness is guaranteed by the theorem of existence. Okay, let's continue. Look at example 6. So I hope you can pause the video and try to work on this one first. Have you finished? Yes. Let's check our work together. So is this guy linear or nonlinear? Oh, you can look at this. This is cube roots, so of course nonlinear. And then let's see. Okay, first standard form, yes. And f of xy is 3x of 5th. This is like 2y minus x squared to the 1/3. Okay, this is f of xy. Okay, this guy is a continuous. Let's see. This is cube roots. Cube roots. Remember, cube roots is continuous everywhere. So this is continuous for all x and all y. Okay, everyone. Okay, and then second partial f partial y. We want to take the derivative with respect to y. So 3x to the 5th stay here. And then this is chain root, right? This is like u to the 1/3. So u to the 1/3, we have 1/3, and then u to the negative 2/3 times u prime. The prime means we're taking the derivative with respect to y. So this is actually 2. Okay, now what do we get? We get 2x to the 5th, and then 2y minus x squared to the negative 2/3. Well, negative means is actually in the denominator. To the 2/3. Okay, so this guy is continuous when the denominator is not 0. So 2y minus x squared is not 0. Okay, it means y is not equal to x squared over 2. Okay, well, what is this guy? This is on the xy plane. This is the parabola. It goes through 0, and when x is 2 squared 4 over 2 2. Ooh, okay, so this is a parabola. Looks like this. So this guy is continuous if y is not equal to this parabola. But you know what happened? You can see our initial conditions is actually on the parabola. So that's why partial f partial y is not continuous at the 2 2. Okay, so we have f continuous but partial f partial y not continuous. So we set existence but not uniqueness is guaranteed by theorem of existence and uniqueness near the point 2 2. Okay, everyone, do you have the same answer? Okay, how about the points y of 1 equals 2? So this is 1 2. You can see 1 2 is right here. Oh, this is good. You can see on the 1 2, then we have f and partial f partial y both continuous near it. So unique solution exists by the theorem of existence and uniqueness. Okay, then now you can see with the same differential equations, if the initial conditions is different, then our conclusions could be different, right? Okay, how about this following? Okay, now what is the difference? Now do you see this is a square root? Okay, so this square root, now let me use a different color. So f is 3x to the 5th. This is 2y minus x squared, right? And so this is square root. So we had cube root. Cube root is continuous everywhere, but for square roots, the domain is when the square root is greater or equal to 0. But remember the theorem of existence and uniqueness. We require f must be continuous on a rectangle containing that point. But this guy is only continuous for 2y minus x squared greater or equal to 0. Greater than 0, because we need f is continuous on a rectangle, open rectangle containing that point, not exactly at that point, right? So that's why we need greater than 0. Then we have y greater than x squared over 2. So this is the parabola greater than, so right here. Okay, so that's why at the 2 2, you can see we cannot have f continuous on an open rectangle containing the point 2 2. So f is not continuous near 2 2. So even though okay, if I zoom in the picture, so this is 2 2. Even though at this part is continuous, but on this part it's not continuous, so we still say it's not continuous near the 2 2, because it's not continuous over the entire open rectangle containing the 2 2. So that's why we still count it as not continuous. Okay, so and similarly we get partial f partial y is, okay, what is that? 3x to the 5th 1/2 2y minus x squared to the minus 1/2 times 2. okay? Because u prime is 2. So then we get 3x to the fifth, and then 2y minus x squared to the 1/2. And of course, this is not continuous as well, okay? So that's why we have f, partial y, they are both not continuous, so we say neither existence nor uniqueness is guaranteed. Okay? By the theorem of existence and uniqueness near that point. Okay, and that finished session 1.3. Okay, so if you have questions, feel free to ask me. Cheers! Bye!